Good day, ladies and gentlemen. Today I am going to talk about adaptation on all possible levels, and I will start from the top. I've been told that the world has changed. I can't really testify to that because I haven't seen much of the world for the last year being in quarantine. But what I know for sure that I am not pacing back and forth on the podium in front of you right now, and you are not sitting in the tightly packed conference room. Rather, we all enjoy the comfortable spaces of our home offices, and that is definitely different. So something has changed, and we have adapted. Why? Because we're humans, and adaptation is the key to our survival. Naturally, some of us have easier time adapting to the new situation, and some might have even welcomed the ability to work from home and not commuting to the office every day. For others, it might have been harder. And similar to us as individuals, different businesses have different easiness when they need to adapt. Uh, Restaurants have to introduce the social distancing. As a matter of fact, I have no idea how people date nowadays. Good thing I'm married and I don't have to. But today, I'm primarily going to concentrate on the industrial manufacturing. And there are a couple of reasons for that. First reason is that this is our target market at Neurala. Second reason that industrial manufacturing is large and it is really hard to change, really hard to adapt. We've been talking about fourth industrial revolution or industry 4.0 for some time right now, but it is really hard to steer industry in the new direction. And in this sense, the old Russian saying that it wouldn't be happy, but the trouble helped is actually reflecting what happens in the industry right now. Due to the pandemic restrictions, industry has to adapt much faster than it used to, and that's what we are seeing. So, what happens? The supply chains have been disrupted. Sometimes factories closed for weeks just because of the quarantine. Sometimes it's just they cannot employ as many people as they used to. They have to introduce the social distancing. Customer demand also changes. Some products that we really cared about a year ago are not so much important. On the other hand, face masks become like really in demand. And I remember issues with finding hand sanitizer back in the beginning of the quarantine. So naturally, not only the production, but also the demand has changed. And the industry has to reflect those changes and reflect those changes quickly. So what do they try to do? They try to adopt new technologies fast and change more rapidly than they used to. They are focusing much more on automation, right? The less workers you can have on the factory floor, the more important it is to have the factory floor automated. They're embracing AI. Before that, it was kind of like hesitation. It's a new technology, not necessarily fully tested. Maybe we should wait a little bit to see that. Right now, AI is basically embraced by industry. And they're looking for solutions that are fast and affordable, as always. So at Neurala, we look primarily at the quality inspection on the manufacturing floors. And what we see here is a set of requirements that we need to satisfy before our system can be deployed. First and foremost, the whole point of the quality inspection is to reduce the production line downtime. If the line starts to produce defective products, the line has to be stopped and fixed. And ideally, the quality inspection will be able to predict before the line actually starts producing defective products. Second, naturally, it reduces the material waste. We can eliminate producing defective products. That means that we use our materials to produce the correct ones. We want to achieve 100% visual inspections. Right now, it is, unless it is automated, it's only so many items that the human can inspect during the day. And we want to reduce the returns and rework of the products. And finally, as I mentioned on the previous slide, the demand has changed quickly in the recent months, and the industry needs to be able to scale up and down depending on the demand. The images here I have in the slide basically show different customer use cases at the bottom that we have been facing at Neurala for the last several months with our product, and I'll go in a little bit more details about that. Basically, you can categorize them in several categories. One is the surface inspection, and it can be brand quality, it can be lumber, it can be sheet metal, painted surfaces. The point there is that the surface needs to have certain qualities, and the system needs to detect if the qualities do not match what it's supposed to be. The second category is primarily packing and assembling individual items into the packages. So we can check whether all the items are packed correctly, whether the pallets have the necessary number of items, and so forth. And finally, the more complex components manufactured, like circuit boards. Here we can check whether all the components are on the board, whether they are welded correctly, and so forth. So it's not that visual inspection didn't exist before, and the machine vision, the classical machine vision, was used for inspection in manufacturing industry for quite some time, but neural networks provide a much more versatile tool for the visual inspection. And why is that? Well, first of all, in the machine vision, the most important feature that determines the success is how good are the features that the system is trying to analyze. And in the beginning, people were handcrafting those features and creating specific feature sets that had to be extracted from the data in order to perform well with the learning algorithms. Naturally, this is a very tedious process and requires lots of experts. So people started to design the feature extraction algorithms that extract the features automatically. But still, those are biased. The same way as when the expert is handcrafting features, the algorithm is biased with the developers of the algorithm of what features are important from the point of view of the developers. And not necessarily those are the features that are most representative for the AI to learn. How did it proceed in neuroscience, where people are trying to understand how the brain works? Well, over there, they understood that the brain actually learns the features from the data. So what they were trying to do, for example, after Hubel and Wiesel discovered that in the primary visual cortex area V1, there are cells sensitive to particular orientations, the modelers started to create neural networks that can learn those particular features, the orientation bars, and the cells will respond to the bars of particular orientation. Now, when it was done, they analyzed and looked at it and said, oh, they look very much like Gabor filters. So now we can proceed to the next visual area, secondary visual cortex, V2, and figure out how the features are learned there, because those are higher level features. But we will just pre-code Gabor filters as our features in the layer V1. And then they proceeded further down, and with each layer, you can have several dissertations that describe how those features are learned and how they can be used on the next stage. And there were two reasons for that. One is primarily mathematical. The bigger and more complex your system is, the harder it is to guarantee that it will converge if you try to learn in all layers simultaneously. And second, the computers were not powerful enough to represent that many cells at once and run the simulations. This all changed when the programmable graphic processors were introduced, and the deep learning systems removed the restriction on how many neurons you can simulate at once. You can simulate huge networks in the current graphic processors, and the system using backpropagation algorithm can learn all the features from the low-level features to the high-level features at once, and the algorithm, generally depending on how you choose the hyperparameters, will converge and provide you a good representation. So if we look at the deep learning neural network in details, what we see is that in the low levels, similar as it is in the brain, we have low-level features. The higher up the network we go, the features become more complex. Later cascades of the network usually have features that start to be object-specific and relevant for particular objects that are in the data set. And finally, the last layer presents us the classification of those objects. But if we follow the brain analogy, we don't need to learn many different data sets. Our visual system is trained using all the visual information that we'll have outside that we look at, and those features are the same throughout our lifetime. So I'm making a statement here, which is the first most important take-home message. The features will stay constant within a domain. If you train your network on large amount of possible visual images that are coming from the camera, you don't need to train low-level features again, because they will be the same no matter what kind of images you present. If you switch to the domain, you go to infrared, or you go to sound, or you go to 1D sensory temporal stream, then it's a different story. But as long as you stay within the domain, you don't need to retrain your features. So now I am going to run a little bit of comparison between different systems that can be used for industrial quality inspection. And I will have 4 competitors here. And the first competitor is human, because so far we didn't find the technology that's good enough to replace. Second will be traditional machine vision. The third one will be the deep learning neural networks as they are out there. And the fourth one will be Neurala design, lifelong deep neural network, as we call it. And I'll compare the 4 and see which basic principles do we need to follow in order to actually satisfy the requirement of best quality inspection. Because the basic features are the key. You can have different implementations, but as long as you satisfy the general requirements, your system will be acceptable for the customer. So what do humans do? They learn from the features of the data. They learn the features from the data. And that's really good, because that doesn't require much of external influence on how the learning proceeds. As a matter of fact, our early visual system learns most of the features in the first weeks of our lives, when we don't even understand the language well enough in order to have some kind of supervised learning. So it's completely unsupervised. And initial training takes a lot of time. For humans, it's usually years and years altogether before we are able to go on the manufacturing floor and start doing the inspection. Look at machine vision. First of all, we need an expert that has sufficient amount of knowledge in the similar tasks that he completed before or she completed before, or an algorithm, again, crafted by the experts that will be able to handcraft our feature set that is particular and specific for the problem that we're trying to solve. The second thing is that it is highly unlikely that we'll get the feature set correctly the first time, so we would have to iterate through it and see which features actually are important and which are not. So it is an iterative process, takes some time to settle down on which features are actually important for a particular task. Now, both traditional deep neural networks and lifelong DNN, they follow the human's example. They learn the features from the data, and also the initial training of those features takes a lot of time. Not as long as humans, not years, but still quite frequently those are weeks that you need to run the particular data set, like ImageNet or something even bigger the better, in order to train your feature sets. So what does it tell us about those four competitors? Well, humans are naturally scalable. If the task changes, you can easily adapt. Machine vision is not so much scalable, because if you need to handcraft features for every task, it means that every task will require a lot of work, and pretty much you cannot reuse anything that you have done before. You need to start from scratch. DNNs and LDNNs, since they learn the features from the data like humans, are also scalable. You just provide new data and you are ready to go for the inspection as soon as the training is done. So what kind of data do we need? Humans usually take huge amount of very general data. We look around, we see whatever we see, and we use it in order to train our visual system. And then at the end, we need to get a little bit of problem-specific data in order to start perform quality inspection, which usually comes something like, hey, youngster, you see this blue tint? That means the polishing system doesn't work correctly. You need to replace it. And that's about it. Single presentation. Well, if we're not smart enough, then probably it will require 2 or 3 presentations from the supervisor or the older coworker, and we're ready to go. For machine vision, well, first of all, we have all the data that's already in the expert's head, and we cannot live without it. And then we need a moderate amount of the problem-specific data. We need more than for humans, because the traditional machine vision is based on statistics, and statistics don't respect the data that has fewer than 30 samples, right? So we need more samples here, and the expert needs to look at those and analyze using the data that the expert has seen before, and as a result, the new feature set can be crafted. What about DNNs? We need a large amount of general data. Not probably as large as humans, although I would presume that if the DNN will be able to see as much data as we do, the accuracy will be even better than it is right now. Plus, we need a large amount of problem-specific data too. We need more data for the DNN than even for machine vision in order to train for a particular task. Just because for each class, we'll better have about 1,000 images. Otherwise, we'll start overfitting. That's inherent problem of the gradient descent based algorithms. So the more data is, the better. What about lifelong DNN? Similarly, we need large amount of data in order to train our feature set. But after that, we're like humans. We just need a little bit of the problem-specific data. We can start with as few as a single image, and then proceed from there. So for humans, it's pretty easy. We don't really need to do much to train their original visual systems, because they already done it for us before they came on our factory floor. Similar for lifelong DNN. The features were trained at Neurala. When you get it on your factory floor, all you need to provide is a small amount of your problem-specific data. It's much harder for machine vision and traditional DNNs, because every customer would need to provide a large data set that can be used either to handcraft the features or to train the DNN. So let's see what is good about DNNs and when does it work well. And unfortunately, it requires some pretty restrictive conditions that we're going to go into details of. First, we need sufficient data for all needed classes, and it has to be collected before the training starts. Second, this data has to be balanced. with equal representations for each class. Third, the conditions at which the data was collected should match the conditions of deployment. And that is quite important. I had this anecdotal case when one of our customers provided us with the training data set. We trained the system. The system had 90% or 95% accuracy. I don't remember what the requirement was. And then the customer started to test it on their floor and came back and said that it performs a chance. And when we looked into it, we realized that the training data was collected by a fixed camera in a particular position, and the images that the camera was taking, the object was occupying about like 75% of the image. While for testing, the customer used the cell phone that was in the totally different position, much further away from the object, and the object was only about 20% of the image. Naturally, the system didn't perform too well. So the conditions should match. And most important, the conditions of deployment should never change. Another anecdotal case here is my VP of engineering has trained the neural networks and validated it in the morning in his setup with artificial lighting, highlighting the object, taking the images from the camera, running it through the system, and getting about 99% accuracy. And then came back after lunch and validated it again and only got 50% accuracy. And all the artificial lighting fixtures were exactly the same as they were in the morning. The only thing changed was that the sun moved outside and was shining from a different angle. And as a result, the system was completely thrown off balance. So deployment conditions should stay the same. And then the DNN will perform well. Unfortunately, that pretty much means that it only performs well in the lab. As soon as you go out and start working with the real world data, it's a whole different ball game, and you need to handle it somehow. So let's look at the individual requirements. Sufficient data for all classes before training. How hard is it? Well, it depends. If you are using Mani's data set, you have 10 digits and you know all 10 digits in advance. If you are trying to do something more real world like, it's a little bit harder. For example, this nice app that was shown in the Silicon Valley series, a hot dog and not a hot dog, right? We know everything about hot dogs and we can provide enough data to train this particular class. As for not a hot dog, I'm sorry, but everything can be not a hot dog. And there is no way you can provide all possible images for all possible objects in order to train this class. So what can we do in order to implement this particular application if we're limited to traditional DNN? Basically, we can set up a confidence threshold. So let's say if a confidence of being a hot dog is above 85%, then it's a hot dog. If it's below, then it is not a hot dog. Might work well, might not. Because, for example, if your system knows not only hot dog, but also burger and the sandwich, it can be the situation that both burger and sandwich, or all of them, hot dog, burger, and sandwich have confidence above 90%. And then what are you going to say? Is it a hot dog or is it not a hot dog? So we need somehow to figure out how we can handle the situations when the image that is presented is not in our original data set, or when the image is presented and is confusing. We have pretty high confidence for more than one object, and we need to figure out which one it is. And ideally, in order to solve this task, we need a system that is able to identify those novel objects and flagging them and reporting them, saying that this is not something that I have seen before. And also, if it is confused, two objects having sufficiently large confidence, again, it should flag it and say, hey guys, here is something very confusing. Can you give me more data? Second requirement, we need sufficient data for all classes before training. And Here on the right, I have the example for the segmentation task. We have an image on top, and we have all those classes with different represented with different colors at the bottom. That's how tagging for segmentation is going on. And we need hundreds of correctly labeled images in order to provide substantial representation of a class. How hard is it? Well, we were working with a cell phone manufacturer, and it took us longer to label the data set. So we got about 100,000 images from them, and we outsourced the initial labeling to the company that does nothing but labeling the data. And then we got it back, and we ran through our quality control internally and corrected some of those images. And altogether, it took, I think, like 6 or 8 weeks to do this. It only took 2 weeks to actually train the neural network that was performing well enough using this data to be deployed on the phone. And naturally, they come to us and say, hi guys, this is awesome. We deployed it on the phone. Can you improve the accuracy for the next version of the phone? And we said, yes, sure. And I have to tell you that most of the accuracy improvement that we got on the system over the next year was looking through the labeling of the data set, finding where the labeling was wrong, correcting it, retraining the system, and the performance improvement was much better than what we could achieve with tweaking the architecture, tweaking the learning rates, tweaking the augmentations, and this kind of stuff. So we need sufficient data, well labeled for all classes before training, and it is sometimes really hard to achieve. We would rather have few images so that we can check that they're labeled correctly much faster, and still the system would be able to perform well. And for that, we need to switch the paradigm in the system. We basically need to replace deduction with induction. Traditional DNN sees thousands of images of the cat and then looks at the new image and says, oh, it's sufficiently close to the cat, so I'll say it's a cat. What we need is to show the image one, or maybe 2, 3 images of the cats. And the system already being able to say, okay, it looks close enough to the cat, so I'll say it is a cat. Then we would be able to train much faster. But of course, there is a problem here that the system that have seen 1,000 images will probably be more accurate than the system that only have seen 3. So what we need to do is to allow the system to correct the wrong inferences and update the knowledge on the fly. Then, even if we're not as accurate after only seeing 3 images, but we add more as we go, and the system becomes more accurate, and eventually it will outperform the original system. So that's about sufficient data. But now what about the data balancing? And unfortunately, here, sometimes it's difficult, sometimes it's outright impossible. So let's go back to the segmentation case again. Let's say we're doing the segmentation of the seascapes. Naturally, the sea, the sky, and the beach will always have in those images more pixels than any other classes, boats, people, building, whatever. So there's no balancing here. We need to take care of that ourselves. If we go to manufacturing quality control, it's much worse, because out of 10,000 products, probably 9,999 are good, and only 1 is defective. Furthermore, every time there is a defective product, it's not necessarily the exact same defect. They're actually probably all different, and we need to be able to recognize them all. So how am I supposed to collect 1,000 images of each particular defect if, in order to get each of those particular defects, I need to run the system for a very long time? Comes pretty much impossible here. So augmentation, artificial data generation can help for seascapes, but cannot help for manufacturing tasks. There are just too few defective items that we can work with. Now, we already said what our requirements are for the ideal system. We need to identify novel objects as being different, and we need to learn through very few images and update the knowledge on the fly. Here is the fun part. If we satisfy those two requirements, we don't need to care about balancing the data. Because even if we have only one image, we already can start learning using our induction. And every time we see a new defect, it's a novel object. So we can mark it and we can bring it into our knowledge using the second item here. Absolutely awesome. So why pure DNN-based systems cannot do this too? There are a couple of limitations that they have inherently, and that prevents us from being able to satisfy those two constraints. First, softmax is only good if you need to predict always. If you have, again, MNIST data set, you have 10 digits, and you know that your system will never see anything outside of those 10 digits, so you always need to make a prediction. In the real life, most often than not, your system will see something that you haven't traded on. And forcing it to make a prediction isn't good. So we see two cases here on the right. And if you scale them as exactly same activations, just different scale. So naturally, in the second case, we would prefer to say, yes, this is an item number 3 here, because it's so much better than the others. In the upper case, we probably don't want to say that, because it's not so much better than the others, if you consider raw activations. So what you can do is very simple. The dotted line here represents the average activation across all nodes, and the dashed line is additively put on top of this average. And additively is important here. If you do it multiplicatively, it will not work. How much better than the average you should be in order to get accepted. And in this case, naturally, in the upper case, you can see that although the object is better represented with these features than all other objects that the system knows, it's still not good enough to cross the threshold. In the bottom case, it's clearly good enough. Now, what if we're going back to our situation where we have a hot dog and a sandwich and a burger, all having pretty high confidences, and how do we choose between them? Well, naturally here our case shows that both of the strong objects cross the threshold. So what do we do here? Well, the system has to report that now it has more than one good guesses, and it's actually confused, and it needs to learn more. Remember, our system is able to update knowledge. So every time it is confused, it can tell you, I need more data. Now, DNN cannot really do it, because for DNN to learn more, it means that you need to take all your original data, add the new data, and then do a complete retraining. Why is that? Because of the catastrophic forgetting. What is catastrophic forgetting? Well, we have distributed representations in our DNNs. That's very good because our representations are really compact, but very many neurons are involved in classification of every single object. And pretty much all the weights in the network are also involved in classification of each object. That means that every time we learn a new image, we are changing the weights in order to adapt to the new image, and it means that we are forgetting the old one. So what can we do here? We need a system that doesn't suffer from catastrophic forgetting if we want to do online learning and add knowledge on the fly. How can we do that? Well, let's go back to our desires. So first, we know that the features stay constant within a domain. So you don't need to change them once learned. That means that you want to train DNN only once for a particular domain. And then you don't really want to keep the upper layers because they have object relevant features and object classes. And if you're going to change the data set, this is not something that you want to keep. On the other hand, the low level features and high level features before they become object specific, that's something that you do want to keep. So you train the DNN once per the domain, and then you chop off the head every time you need to adapt it for a new data set. Once again, so we have our backbone, which can be the same for different tasks within the domain. And we have seen this before already. Like you can take MobileNet, you can train it on the ImageNet, and then you can use it in the detection framework, in the recognition framework, and even in segmentation framework. What it does, it extracts the features that can be utilized in any of those tasks. The complexity of the backbone depends on how fast you want the system to be and how accurate you want it to be. And the primary job is just to extract and organize the features from the data that are important. That's it. Then we have the head, which we can change with every particular task. The complexity will depend on the task, whether it's detection, segmentation, or classification. The complexity will be totally different. And the primary job is to solve the task. And this is the only part of the system that has to be data set specific within the domain. So what are the requirements for this head? First and foremost is that it has to be able to consume the feature vectors out of DNNs as input, because otherwise we will not be able to put it on top of the backbone. We would prefer one-shot learning. Why? Because we don't want to collect too much data. We would prefer the learning time and memory profile not to depend on the number of learned objects, right? The simplest head that I can come up with will be a lookup table, but the lookup table will grow every time I add something, and eventually it will become unbearable. We want learning not to require any prior knowledge, and that's a stone towards the Bayesian systems that do require some priors. We want learning not to affect the old knowledge, and that is the trouble that we just saw with the backpropagation-based DNNs. We want minimal dependency on the input order, right? We're trying to do one-shot learning here with a very few images. We know that neural networks tend to overfit when they don't have too many images. So if we have an image of a cat, an image of a dog, and an image of a rabbit, we want to be able to present them in any order and get the same outcome from the system, no matter which order we presented to them. We need to have a good generalization from a few examples. Naturally, lookup table doesn't fit here also because it doesn't do any generalization. So we need some kind of system that is able, from seeing one picture of a cat, to be able to recognize similar pictures of the cat at least. We need to handle the unknown objects gracefully, preferably marking them as something that the human needs to look at and maybe train the system additionally for those objects. And the inference time shouldn't also depend on the number of learned objects. I've seen some systems that satisfy many of those requirements that have either learning time or inference time growing exponentially as the number of images, as the number of objects the system learns. And that's not good, because that would limit the amount of knowledge that the system can consume. And I have a bad news for you. I am not aware of any learning system out there that can satisfy all those 9 requirements. So until somebody comes up with the system that does, the best we can do is to pick the system that satisfies some of those. The more the better, like 6 or 7 would be nice, and then use it for something like our lifelong DNN. Keep improving as you go. So Whatever we have right now, based on the basic principles that I outlined, LDNN can learn a class from a single image. We can provide it all the examples of class A and then all the examples of class B, single presentation each, and learning class B will not disrupt the learning of class A. We can add, because of that, any new objects or update existing objects at any time. Training time is the same as inference time. One-shot learning doesn't differ much. We don't need to run multiple epochs. Although for current system that we have, it does increase linearly when the number of classes the system knows. So that is one of the requirements from the previous slide that we fail for now. The system can respond nothing I know for the inputs it doesn't recognize. And we have one extra feature for free, that knowledge from two different heads that are trained with the same backbones can actually be merged together, and we can create a head that knows both sets of data from the original two heads. And we can also use the same backbone with multiple heads trained for different tasks. So we get a single image, and we can run classification backbone to do the whole scene classification, or detection head in order to determine where in the image the object is, this kind of stuff. Now, but if I was an academia here, I would stop and publish a paper and tell everybody how great I am. But in reality, I'm running a business, and nobody really cares what can LDNN do for me. What customers care out there is what can LDNN do for them. So this is the question that I must be answering here. So I'm going back to our competition now that we know a little bit more about basic principles of lifelong DNN. We can complete our run. So that's the previous slide that you have seen before. Different amounts of data that the systems need. What else? What happens if the conditions change? The lighting changes, the system is deployed on a different manufacturing line, or the manufacturing line changes the SKU. Human need a little bit, if any, amount of new data. If just the lighting change, human doesn't need anything. Our visual system adapts pretty nicely. If the SKU changed, we just need to get the information of what are the correct versions of the new one, and then we will be able to detect the defectives. Machine vision, we pretty much need reanalyze, at least if not rewrite the whole system, because we handcrafted our features for the previous SKU and previous lighting conditions. Now lighting conditions or SKU changed. We need to make sure that the old features are still valid, and if they are not, design the new set of features based on the new amount of problem-specific data. Naturally, we need to recall the expert that did the original system, because if we cannot, then in addition to that, we'll have hard time figuring out what the old system was doing before we can modify it. DNNs, we need is large amount of new problem-specific data for another fine-tuning, right? I'm not talking here trainings from scratch. I'm taking the talking about the transfer learning, where the system was pre-trained on something like ImageNet, and then we just fine-tune it on the new data. Or if it's something as simple as the lighting change, we might play with the pre-processing. We might change some augmentations. We might change some filtering of the input. We might be able to compensate for the lighting changes, but I would guess that we would still need a little bit of fine-tuning to regain the accuracy back. As for lifelong DNN, well, again, we just need small amount of new problem-specific data, same as before. We can keep the previous knowledge in the system. We can wipe it out. Doesn't really matter. We don't need to retrain the backbone. We're only retraining the head. The training is fast. We can adapt the system pretty quickly. So again, for humans and for lifelong DNNs, solution is easy. For machine vision and traditional DNNs, requires much more data and therefore much harder. Finally, one last item of the competition is, what about 24/7 operation? And here is where the humans get tired. I cannot look at the same item again and again and again throughout the day, not to mention that after 8-hour shift, I need to go home. Somebody else might replace me, and we are different, and we're all objective, well, trying to be objective, but we're actually subjective. So how do we get the objective score from even two different people? It's not so easy. On the other hand, machine vision doesn't need to do it. DNN has no problem. Lifelong DNN has no problem either. They can run 24/7 as long as there is power to the computer. They are not getting tired. That's awesome. So, hard for human, easy for the machine. If we go back and combine all the competition that we did so far, we have a clear winner, which is our lifelong DNN that follows the basic principles that I outlined in this talk. Human is a close second. The only thing that human cannot do that LDNN can is to work 24/7. And traditional DNN is finishing in the third, just because it requires much more data than the other two, but less work than machine vision, which is clearly a loser here. So now I'll switch to some customer-specific requests that we've seen in the recent months to show you why customers are interested in our LDNN solution and why they're talking to us and buying our solution. The first feature is for missing items or defective items. We have multi-head LDNNs that allow to look at each individual item and identify it as either good or no good, missing or defective, at a computational cost of a single DNN. So for example, you see those 4 production line here, the bottles there are different. So we can set the exact same system on all 4 of those. They will run through exact same backbone and producing us the feature vectors for all those 4 manufacturing lines that we will split into 4 different heads trained on different kinds of bottle here, and basically running a single DNN with just 4 small heads, we will be able to do the quality control on all 4. Another thing is that we can learn from only good images. So for example, in the upper picture, we can learn from the eggs and never even see the empty slot. But the system would be able to recognize that there is no egg in this slot and alert. And you can do it 2 different ways. You can take the whole picture and then the system will be saying that you're missing an egg. Or you can split this picture into individual cells, feed it through the system as a batch, and then it will say you exactly which egg is missing. And this is especially important for the customers that have high SKU counts or rapidly changing. Like for example, at the bottom image, you have red pills, blue pills, and green pills, and blue-red pills. And if you train the system on just red and white, it is basically just extra few seconds to turn it to learn additionally blue-white and additionally green, and then it would be able to do the quality detection on all 4 of those SKUs instead of just 1, without significant training, and actually still using the same backbone, just different heads. So to conclude, the traditional DNNs do miss some critical requirements for wide adoption in manufacturing. And I have shown you that if you follow 3 basic principles, right, the features are staying the same. We need to be able to recognize something that we don't know, and we need to update our knowledge as fast as possible without retraining. If you follow those 3, you can create a system that is similar to our LDNN, and you will be able to solve the problems that I outlined in my talk today. The key is You need to learn fast with little data and continue to learn as the new data becomes available. Then you will be able to adapt your system to whatever manufacturing needs are and help manufacturing to adapt what the needs of pandemic world are and help us to adapt to our environment as we always do in order to survive. Thank you very much.